Greeting viewers, and thank you all for watching our abstract video. I hope you are all doing well. In this video, I will briefly summarize our paper, which will be published in Journal of Navigation. First, let me introduce myself. My name is Rolla Pervizi, and I'm currently a position algorithm engineer at Hemisphere GNSS. Our paper title is Surface Reflectivity Variations of Global Navigation Satellite System Signals from a Mixed Ice and Water Surface. I'm grateful for the contribution of my collaborators, Shahrukh Khan, Dr. Alison Bandwell, and Professor Subhani Dattawarwa, who helped me with this research. Our paper is structured as follows. It starts with introduction. In the introduction section, we examine the reason behind the utilization of GNSS for reflectometry, highlighting the advantage and disadvantage compared to the existing methods. We also outline the goals of our research. In background and GNSS reflection, we provide a brief overview of the GNSS signal reflection, the underlying physics, and we introduce surface reflectometry. Next is method, which we explain our methodology employed in our study, offering insight into data collection, our sensor suite, location and environmental condition of data location. Then we go to the results section, which presents our research finding and outcomes of our study. In the discussion section, we provide insight analysis and interpretations of our findings. Finally, we draw conclusion based on our finding and research outcomes. It has been demonstrated that GNSS reflected signals contain valuable information about the surface from which they are reflected. In addition, global coverage and widespread availability make GNSS an exceptional source for remotely sensing Earth's environment. In this work, we seek to investigate the feasibility of using GNSS-R to distinguish ice from water. To find the answer, as we described in this cartoon, we set up our sensor suite at the front shore while the lake surface was a mixture of ice and water. We collected GNSS reflected signal, especially GPS L1 in this case, and processed them further at the lab. A GNSS signal reflecting from the surface of ice or water is dominated by specular reflection. The specular point is here, is the point at which the angle of incidence equals the angles of reflection. Most of the energy is scattered from an area around the specular point known as the first Fresnel zone, as shown in this figure. For more detail, please visit our paper. To discriminate ice from water using GNSS-R, the surface reflectivity SR is used as a detection metric. Surface reflectivity SR is the ratio of incident signal power to the reflected signal power. SR is related to the receiver SNR by ballistic radar equation, which provide equation 1 provided here. In the method section, we describe our sensor system, the location and condition of our data campaign, and the post-processing steps which we use to estimate the surface reflectivity SR of ice and water. This figure shows a schematic of our sensor system. Our sensor system includes two GNSS antenna, one for direct and one for reflected signals, two USRP devices for collecting as a front end, a Lidar sensor, 3 cameras, and 2 network switches, and a power source. The system has been used for 11 data campaigns from 2017 to 2020, which most of them were in the winter season. Figure A shows a photograph of the sensor system on site and lake surface condition from the data campaign that occurred on February 2020. Figure B shows a Google Map satellite image of the field test in Chicago on the shore of the Lake Michigan. So B hat here shows the direction of the arm or the boom of our sensor suite, and mu is the angle from the north, angle between the boom and the north direction. The post-processing workflow for computing and comparing the GPS SR with the optical mean red value are shown here. For more detail, please visit our paper. You can find it in section 3.2, which we describe in detail our post-processing. So this figure presents a combined image of the camera 2 and 3 projected to the east-north coordinates relative to the reflection antenna. In this figure, the green cross here indicates the reflection antenna origins. Orange dots here marks the specular points. The Fresnel zone, the first Fresnel zone of the PRN 8, 16, 26, and 27 are shown in this figure, shaded in light transparent red. The relative SR and mean red value for PRN 26 are displayed over time in the figure at the top. The UT hour and minutes are shown on the horizontal axis. The left vertical in the blue is the SR in dB relative to the SR at the initial time. The vertical axis on the right in the red is the mean red value during the same data time period. The bottom figure plots the SR versus mean red value. For PRN 2016, the correlation coefficient is 84%. In conclusion, we correlated the GNSS SR, GNSS reflected signals SR with camera image to assess whether GNSS drive SR can distinguish ice from water. Results from Lake Michigan data campaign held in Chicago, Illinois in February 2020 are presented in this work. During the field work, the lake surface consists of mixed ice and water. The SR result of PRN 16 and 26 are well correlated with the camera's RGB red value. The SR of PRN 27 shows poor correlation with camera RGB red values over 40 minutes. We attribute this low correlation to the surface scanned by the first Fresnel zones of the PRN 27 being heterogeneously ice and water within Fresnel zone. We conclude that the SR of GNSS reflected signal can likely be used to distinguish ice from water. Our aim is to expand this work to be able to test detection of the surface melt condition on glacier, ice, and snow. In future, we will study additional data sets that includes the condition of both ice, surface ice, and water, including those in glacial in Antarctica. In the end, I would like to thank Lee Penn, David Stewart, and Aura Lopez for on-site help during the data campaigns, and Christian Larson and Douglas McHale for their advice and support. I also thank the Chicago Park District for providing the research access to permit for all field testers. This work was funded by National Aeronautic and Space Administration Award NNX15AV01G, National Science Foundation NSF Award 1940483 to Illinois Institute of Technology, and NSF Award 1940473 to Illinois to University of Colorado Boulder. I appreciate your time and attention in watching my video. Thank you all. Additionally, you can reach me via email at ruhollah.parvizi@gmail.com, with my first dot last name at gmail.com, for any question.